Hi folks! Today we're going to look at how the first and second derivatives can combine and give you a good idea of where max and min values are. So to start with, we'll look at a couple of investigations. We're going to draw a smooth curve with a min on it. So you can pull out a piece of paper, pause the video, draw any curve that has that property. That'll be its only extreme value. And then do the same thing with a max. So I'll try one here. Here's with a min on it. Okay, here's one with a max on it. And if I look at those extreme value points, like this one right here, there are a couple of things I can notice. Number one, it's horizontal at that point, or its first derivative would be 0. So it's horizontal. F prime at whatever that value is, let's call it A, is going to be 0. Same thing with the max. Horizontal, F prime is going to be 0. And that's no surprise. We've been hunting down those critical values of the first derivative for a while to find max and mins. But the other thing you might notice is that this is concave up. And I don't think there's any way that you could have drawn it and had something that was concave down but had a smooth min on it. So it's concave up. In other words, the second derivative at this point is positive. And this one over here, it's concave down. So at that point, the second derivative is negative. If you have these two properties, they automatically tell you that you've got a minimum value. A horizontal but concave up situation is a minimum. A horizontal but concave down situation is a maximum. Which sounds like a lot of counterintuitive stuff to memorize, so we'd probably already sketch it. But this is the big idea for the day. Now let's be clear, we can already find max and min values. We can make a sign table on the first derivative, and that can locate max and min. But there's an alternate test for a max or min that involves the second derivative. And this is basically how it works. If you go through your first derivative and you find a point at which the first derivative is 0, then you can use concavity to help determine whether that's a max or a min. And that might spare you from having to make a sign diagram. So when it says this here, suppose at some point where x equals a, some value, we find that f prime at a is 0. That means we've found a point where it's horizontal. So if you're at one of these horizontal spots, and then you find out also at that spot that f double prime is positive, that means you're concave up. Let's draw that. If you're concave up, and you're also horizontal, this must be a minimum value. Similarly, if you find that you're horizontal and f double prime is negative, that means we're concave down. Must look something like this, and we must have found a max. Now I urge you, don't try and memorize these things where up means min and down means max. It's super counterintuitive. We can always just make the little diagram. Let's try it in the context of an actual function. We can try this new technique on a cubic like this one here. We're going to differentiate and find all the extreme values, so that's local max or local min. Of course, it's going to go up and down forever because it's a cubic, but let's see what we get. So first thing we'll need to do is differentiate. So this will give us 6x squared. This will become negative 5x. And this will become positive 1. I can set it to equal 0, but the simplest thing to do here is just to factor it. So by guess and check or some other method, I'll figure out that it is 3x minus 1, 2x minus 1, and that's going to give us some critical values. These critical values are the places where this curve is horizontal. So they might be a min or a max. Now, we could go and make that sign diagram on the first derivative and figure out which one they are, but this is asking us to use the second derivative to figure it out. So if we want to use the second derivative, we better figure out what the second derivative is. So y double prime will be 12x minus 5. And here's what I'm going to do. I'm going to figure out what the concavity is at x equals a third. And then I'll repeat that for x equals a half. So at x equals a third, y double prime would be 12 times 1/3 minus 5. Or 4 minus 5, which is -1. It really doesn't matter what the number is. What's important here is that this is negative. So that means we are concave down. Let me draw that. Concave down. Oh my gosh, that must be a max at 1/3 something. I'll find the y value in a second here. Now I'm going to figure out what's going on at x equals a half. At x equals a half, what is the concavity? So I'd have 12 times a half minus 5, or 1. That's a positive number. The second derivative is positive. Remember, second derivative determines concavity. So at this point, we know that we're both horizontal and concave up. Let me draw that. Concave up and horizontal looks like this. Oh my, that is a min at the x value of a half. Now to figure out the corresponding y values, I think probably what you want to do is just put them in your calculator when you plug them into the original function. What you're going to find is that this min happens at about at exactly negative 3.875. And this here, this max, occurs at negative 3.87. There's not much in the difference. If I had done this with a number line and a sign diagram, these values are pretty tight together, so it becomes a little bit difficult. But we'll look at that as soon as we take a look at this on Desmos. When we look at the graph of the function, it doesn't even look like there's any extreme values at all. But if we start to zoom in a little bit, they start to reveal themselves to us. And there is that max at 1/3, negative 3.87, like we expected. And here is the min at 0.5, negative 3.875. But more important than that is the fact that at that max, you can see that it's concave down. And at the min, you can see that it is concave up, just like we showed. So it all looked good on Desmos. It confirmed what we expected. If we hadn't done it this way with the second derivatives and the concavity, we could have done it just how we found maxes and mins before. And just really quickly, here's how that looks. You would set up a number line on the first derivative. You'd sub in values, so if I put in 0 to this, I'd get a negative times a negative. It's positive, that means increasing. If I put in a number between a third and a half, like 0.4, this one here would be positive, this one here would be negative, so we'd get decreasing. And right away we know we went from increasing to decreasing. There is a max at 1/3 something. If I put in, say, 1 into this, I'll get positive times positive. It went from decreasing to increasing. There is a min at a half something. And we've already done the math on those points, so we know where they are. This is negative 3.87, and this is negative 3.875. I don't know which way is easier for you, but we are responsible for both approaches. If it doesn't specify the method, though, do whatever works best for you. Sometimes we're only given pieces of the puzzle. So in this case, we're told g prime of 2 is 0, g double prime of 2 is negative 3, and somehow we're asked to say what's happening on g of x at x equals 2. And your initial inclination might be to say, oh, I don't know. But if we start to decode this, it's telling us some important things. If g prime of 2 is 0, then it has a slope of 0 when x is 2. So let's say that. At x equals 2, slope of 0. And a slope of 0 also means that it's horizontal. Over here, where it says g double prime of 2 is negative 3. The 3 might not mean a whole lot to us, but the negative sure should. At x equals 2, we know that it is concave down because the second derivative is negative. So let's draw that situation. Concave down and a slope of 0. Oh my gosh. What do we have? We have a max. That's the only thing it can be if it's horizontal and concave down. And we have a max at x equals 2. Now at this point you might be inclined to put in the original function and figure out the y value, but they never even told us what the original function is. So we can say where the max occurs, but we can't give its corresponding y coordinate. One thing to note about this second derivative test for a max or min is that sometimes it's inconclusive. And if it is, then you'll just go back to the number line on that first derivative, and that will hopefully find any max-min values that you want. So in certain circumstances, using the second derivative is going to be helpful because maybe the critical values are tightly packed. Maybe it's easy to find a second derivative. In other cases, you'll stick to the first derivative because it will be easier to deal with it that way. So let's check this one out. We've got f of x is x minus 2 all to the power of 4. We can differentiate it. We actually looked at this question on the last video. So f prime is going to be 4, x minus 2 to the 3. There's an inner part to this, so times 1 from the chain rule, or f prime of x is 4, x minus 2 to the 3. I know right away from that the critical value is 2, and it causes slope to be 0. So with this second derivative test, what we would do next is check the concavity. So check concavity at x equals 2. Okay, and to do that we need the second derivative. So I'll differentiate again. F double prime is going to give me 4 times 3 is 12. X minus 2 now squared times the derivative of the inner, which is 1, or 12 by x minus 2 all squared. If I check the concavity now at 2, that would mean plugging 2 into the second derivative. Okay, so 12, 2 minus 2 all squared. Oh no! It gives us 0. So we don't know if it's concave up or down at this point. Since this second derivative test is inconclusive, we're going to go back to the first derivative. So I'll do that in a different color just to show it's kind of a different approach. I'll talk about f prime and f. I've got a critical value of 2. And I'm forgetting all about this concavity nonsense. Going back to here, if I put in, say, 0 into this first derivative, I would get a negative, so it's decreasing. If I put in, say, 3, I would get a positive, so it goes from decrease to increase. Ah, there's a min at 2 something. Okay, and I can plug it back into the original and find out that the coordinates are 2, 0. We can double check this on Desmos. Here's that quartic, and you can see that it does have a minimum, just like we found with the first derivative test. But the second derivative didn't help us out that much in this case. There's another piece of graphing software that's kind of helpful that exists for iPad and for iPhone called Good Grapher. And I want to look at this function just briefly in that program because it's got some helpful stuff. So Good Grapher is not quite as user-friendly, but I can put in this function and save it. And it's going to graph the function the same as Desmos does. But something neat happens. If I go and pick a point, like where x equals 2, it tells me the y value, the first derivative, and the second derivative. You can see it in the left there. And that tells us why the second derivative didn't help us out here. So when x is 2, the y value is 0. That's kind of irrelevant. The slope is 0. Of course it is on a smooth max or min. But the second derivative is also 0, which is why we had struggles to use the second derivative test for a max or min. In the end, it doesn't matter which technique you use to find a max or min. But we do need to understand that if you have something that's concave up and horizontal, it must be a smooth minimum. If you have something that's concave down and horizontal, it must be a smooth maximum.